Okay, we're moving on to 33. Now, some of these problems aren't directly achievable using permutations and combinations, so you just have to be careful. So 33, we'll do both of them. It says how many cards must be drawn without replacement from a standard 52 card deck to guarantee the following: 2 cards of the same suit. So it's kind of like a minimum. So let's say you have 52 cards. Step 1, pick a card. Step 1 is to pick a card, and so the result is going to be one of the 4 suits. So it's going to be, let's say, hearts. Let's say, well, there's hearts, there's diamonds, there's spades, and there's clubs. And I'm just going to copy this thing down 5 times. Okay, so step 1, let's say pick a card. It's a heart. Okay, step 2, if you pick another heart, then you're done. Okay, so if we don't pick a heart, then we pick a diamonds, or any one of the other 3. So that's 2 steps. 3 steps, again, if I pick either a heart or a diamond, then I'm done. So the only way I can keep going is if I pick either a spade or a club. Okay. Finally, well, not finally, next last, step 4, if I've chosen these 3, then there's only 1 left that I can choose and still not finish. And so finally, my step 5, I'm going to have to choose, is going to either be one of these 4, and therefore I will duplicate it. So the answer is 5 cards. You know that if you pick 5 cards, at least 2 of them are going to have the same suit. So then you can do the next part of the problem, which says 3 of the cards will be of the same suit. So how does that work? I'm trying to think if there's a. I think in this case you might want to do a tree diagram. So you'd have hearts, diamonds, spades, and clubs. Okay. So I'm just thinking about this one. Yeah, actually, it's really just a continuation of this particular one. You know, by the time you get to the 5th step, then you're going to have at least 2 that are of the same suit. So let me just grab one of these, and we'll just keep cloning it. Infinite cloner. Okay. So there's one more. That's 5, 6, 7. There's another one. That's 8, 9. Okay. So again, if I pick hearts, I've got 2 that are hearts. Now, if I go to the next time and I pick hearts, then I'm going to be done. So I have 3 choices I can make that would not be a heart. So I pick that one. And then likewise, I pick this one to get, so that these are all the cases where I have 2. And then finally you get to this point. And at this point, if I haven't already achieved 3 cards, so if I'd chosen diamonds here instead of spades, then I would have stopped there. So only after this many am I sure that I'm going to have at least, no matter which one I pick, I'm going to have 3 of each particular one. So that's 9 cards. So it's really the same kind of basic philosophy. Okay, 36. Radio stations in the United States have call letters that begin with K or W for west or east of the Mississippi, respectively. Some have 3 call letters. Assuming no repetition of letters, how many 3-letter sets of call letters are possible? Count all possible, even though practically some may be inappropriate. So you've got 3 letters. And what you do is and for the first letter you have W or K. So that's 2 options. Now the remaining ones you're going to have, so we can't, once you've used W or K, then you can't use it anymore. You can't use them again. So in this one we have a choice of 25 letters. And then the next one, we will have chosen 2 letters, so there'll only be 24. And you can actually write this. This is 25 things taken 2 at a time. So this part is a permutation. That's why it's included. But really, we can solve it just using the fundamental counting principle. Because what we have here is, this is 25 factorial divided by 23 factorial. 25 minus 2. And that's 25 times 24 times 23 factorial divided by 23 factorial. These cancel out and you just have 25 times 24. So just take 2 times 25 times 24 and you get 1200. That's your answer. Okay, 39. I think that's next. 39. The Coyotes, a youth league baseball team, have 7 pitchers who only pitch, and 12 other players, all of whom can play any position other than pitcher. For Saturday's game, the coach has not yet determined which 9 players to use, nor what batting order will be, except that the pitcher will bat last. How many different batting orders may occur? Okay, so we have so how many batting? What do we have here? We have 8. There are 9 people on a team, and there are 12 people. So you've basically got 8 spots for the 1, 2, 3, 4, 5, 6, 7, 8. You've got 8 spots for the non-pitchers, and those 8 spots have to be filled by 12 players. And then you've got this additional separate one. You've got 7 pitchers, and there's 1 player. Just 1 out of that. And here we have 8. So it says so it's the order is important because it's a batting order. So we don't use combinations, we use permutations. So we have 12 non-pitchers, and we have 8 slots. So that's the number of ways you can arrange the 8 people, and then you multiply that by 7, just the number 7, because you've got the additional pitcher to choose. So we take 12 factorial divided by 12 minus 8 factorial times 7. So 12 factorial divided by 4 factorial times 7. It's actually going to be a pretty long situation here. So we might just use, well, I don't want anybody to have to think they have to buy a calculator. With factorial, you just got to do a long multiplication problem. But so that's 12 factorial and times 7. So these cancel out, and then you just have to multiply all the numbers together. 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5, and then the whole thing times 7. And so we get 1,397,088,000. So that's 139 million different batting orders. Okay, I'm going to go to 44. So it says we're dividing people into groups. How many ways could 15 people divided into 5 groups of 3 people? So what we're going to do is we have 15 people, and you are going to, basically we're creating these 5 committees. And so we're going to put 3 people in this one, we're going to put 3 people in another one, 3 people in another one, 3 people in another one, 3 people in another one. So the way this works is you're going to, each one of these is going to be, yeah, so let's explain how this works. So the first thing you would do is you would pick 3 people out of the 15 for the first group. And because the order is not important, we're going to use combinations. So it's going to be 15 things 3 at a time. Okay, then you choose the next one. So these numbers are how many people you have available. The second group, you're going to have 12 people available to choose that. So this is the second step. So then you're going to take 12 people and choose 3 out of those. Let's see how many different combinations there are. Okay, then you go to the next step. You've only got 9 people left now. So again, you're going to pick 3 people out of those 9. So you take 9 things taken 3 at a time. Then you go to the next case. You only have 6 people to choose from for those 3 slots. So you take 6 things taken 3 at a time. And then finally, 3 things taken 3 at a time. So that's the numerator. Now, if order was important as far as these groups are concerned, then we would just stop and that would be it. But because the order of these subcommittees is not important, then we have to take that into account. And so each one of these is considered a separate entity. And so the number of ways these 5 separate things can be arranged is going to be 5 factorial times. So we divide by 5 factorial to get the final answer. And each one of these you can do, you're going to have here, so we got, it's kind of long, but let's just go ahead and do it. So this is going to be 15 factorial divided by 15 minus 3 quantity factorial times 3 factorial. So that's 15 times 14 times 13 times 12 factorial. 15 minus 3 is 12 factorial times 3 factorial. These cancel out, and I'm just going to multiply it out. We only got 4 numbers. I get 455. Okay, then I do 12 things, take it 3 at a time, so that's 12 factorial divided by 12 minus 3 factorial times 3 factorial, which is 12 times 11 times 10 times 9 factorial divided by 9 factorial times 3 factorial. Let's cancel out. So I get 12 times 11 times 10 divided by 6. I get 220. Okay, the next one is 9 things taken 3 at a time in combination. So you have 9 factorial divided by 9 minus 3 quantity factorial 3 factorial, just 9 times 8 times 7 times 6 factorial divided by 6 factorial 3 factorial. These cancel out. So I get 9 times 8 times 7 divided by 6. And I get 84. And then we have 6 things taken 3 at a time. So that's 6 factorial divided by 6 minus 3 factorial, 3 factorial. And so that's 6 times 5 times 4 times 3 factorial divided by 3 factorial, 3 factorial. So that's going to be 5 times 4 times 3 divided by 6, just 10. And then 3 things taken 3 at a time. So that's 3 factorial divided by 3 minus 3 factorial times 3 factorial. That's 3 factorial divided by 0 factorial. 3 factorial. 0 factorial is 1. And 3 factorial over 3 factorial is 1. Okay. And then we have in the denominator, we have 5 factorial, which is 5 times 4 times 3 times 2 times 1, which is 120. So our final answer is going to be 220 times 84 times 10 times 1. I think I'm missing a number here. Oh, there's another one. I had 455 at that at the beginning. 455 all divided by 120. 455 times 220 times 84 times 10 divided by 120, and I get 120. Something's wrong. Oh, it's because I didn't do the math right. Let's try again. I get 700 and miss it by a factor of 2. Let's see, what did I do here? Did I miss a 2 out somewhere in my calculations? 15 times 14 times 13 divided by 6, 455. 12 times 11 times 10 divided by 6, 220. This one number here looks kind of out of place, so maybe that's it. Yeah, that's where it is. So this is 30 times 4 is 120. 120 divided by 6 is 20, not 10. Okay, that's where the factor 2 came in. You do that, and you get $1,401,400. So there's the different combinations there. Okay, so we're going to stop for that right now.